feed into your syntactic analysis, which was our context-free grammar. You had our intermediate code generation that can either be, by way of an abstract syntax tree. It can be by way of an abstract syntax tree where we just, recursively traverse the tree and spit out some, fake assembly language, which would eventually get turned into a real one. Or we can, jump straight from abstract assembly tree to code generation. Throughout all of these stages, there's this symbol table off here to the side, which are used. It's used in different forms by each of the stages, so it's slightly different. But basically, what it is a get-out database in order to save just the information that that stage needs to know about. So in the lexical analysis, it would have a mapping of here's my tokens and here's my actual identifiers or int literals and stuff like that. In the syntactical analysis stage, let's see what we have in there. Don't know at the moment. In the intermediate code generation stage or code generation, it would keep information about. So I said before that these object files, which are output by the compiler, are not standalone. They can have reference to data outside of themselves. So in the code generation phases, the symbol table would hold information about, like, here's the symbols which are outside of myself, which I need resolved later by the linker. And that's why, and actually, I think that's in the next stage as well. So that's why, so the symbol table, which I put this little dotted line here, the symbol table ultimately can find its way to the object file. And the information which finds its way into the object file is specifically there to help the linker go find stuff for it. So it's one, to help the linker find symbols which are undefined within the given object file, and two, in some small specific cases, the assembly which you output will actually be devoid of addresses, for instance. Like, you may put a move instruction, and there may be an address that's basically like a placeholder address that says, all right, I'm going to put an instruction here, but I don't know what this address is going to be when the combined file gets generated. So dear linker, fill in this address later on in this actual x86 assembly instruction. Fill in those 4 bytes for an address. Here's the mapping of things which you better fill in later if you want the code to work. So compiler says to the linker, give me these symbols later, and oh, by the way, I generated some assembly code, but it's not done because if stuff gets moved around in the splicing phase of the linker, then, something that may have been at offset, 20 in my object file may be at offset 220 in the final file, right? So you got to fill in those real addresses later on. All right, so we're just going to do a quick basic look at the symbol file for purposes not so much for the filling in, addresses that the compiler can't resolve at compile time, but more about the addresses of symbols. Actually, this is all just what I just said about why there is this need for the object file to have symbol information saying, please linker, fill in this information later. It's just about things which are outside of this object itself. The main point here, yeah, and unfortunately, since my code folder is empty, I can't actually show the code for this. This is unfortunate. I can skip it for this. All right, so in the case of, this is an ELF example. So on the Linux side of things, basically, well, the long and the short of this code, this simple Simon III, is that it was a simple file that imported a function getPy from, so there was one file main and one file pyman.c. And getPy function is implemented in pyman, and simple Simon just calls getPy. Now, the point is, the getPy is implemented in a completely separate .c file, right? So when the compiler turns those two C files into object files, the simple Simon thing, which has main, it knows that it wants to call getPy, but it doesn't know where it actually is. So that's what this is. This is, the putS is like a printf. So there's a printf, there's main, there's a printf, and there's getPy. Simple Simon, does have main. It did implement main in its own, simple Simon III.c. So it says, I can find that symbol within myself. But for something like getPy or something like putS, which is the printf equivalent, the object file itself actually says, look, this symbol is undefined. GetPy is something I need, but I don't know where to find it. So it's undefined. Linker, try to resolve undefined symbols later on. And similarly, the pieman says, I have pieman, right? And so the linker's job is to take these two files and say, well, this one wants getPy. Where's getPy? In this one. And so when it splices together the code and data and all that stuff, it needs to try to resolve all the symbols. But we know that, for instance, the putS, which is the printf equivalent, that's not implemented in either of these two files. So then it can go ahead and say, well, is this putS in any of these libraries which I can potentially dynamically link to, right? And so it goes through the list and says, oh, I see that putS is in your standard C library. Go ahead and just mark that as something the loader should figure out later, and it should import the standard C library. So that was the case with else thing. Very simple. Just you can see right in the printout, undefined. In the case of PE files, it's just a little more complicated in that this is the simple Simon third.obj. There's the symbol table which has these are all the symbols in my file. So the first one is this _main, and so we see short name _main. And it says the offset, the value is 0 bytes into the section.txt. And so this means this is defined within this object file. But these things like printf and getPy, the value, the offset, it's saying it's 0 bytes in, but the section number is 0. So it's saying like, the section number must be greater than 1 if it's actually within this file. So by having a section number of 0, it's saying this symbol is not within my file. I need the linker to go find that for me at link time. So, section number 0 for getPy and printf. And if we go look at pieman, it has getPy and it has an offset of 0, but it's in a specific section, so we know that this is implemented in this file. So between the two, the linker would splice them all together in order to make sure that for simple Simon executable, you can call the getPy function, which is implemented in this separate object file. All right. All right, well, those slides are all old. I really thought I put new slides at the very end. Because I had to, actually, hold on a second, let me see your slides. What did they print? Yes, see, your slides that are printed out are the updated slides, and that's what I put into my transfer folder. Oh well. All right, so time to move along to the PE format. Now, I guess I should ask you a few questions. Before we move on, is there any questions about the stuff that we've covered so far at a high level? Things like this object file splicing together that I just talked about? Yes.
What about position independent code and relocators?
We're going to talk about relocations of position independent code if we get to the ELF section, because Windows doesn't generate position independent code, so it's always it always requires relocations. We'll talk about relocations a bit at the end of the PE format, and if we have time, we'll talk about the exact same thing in ELF. But any questions on the abstract assembly trees, how we walk nodes of this and spit out the same assembly for the same node for a given tiling strategy? Questions about abstract syntax trees and how that recursive code there was able to traverse the abstract syntax tree and spit out pseudo representation? Any questions about context-free grammars, parse trees, syntax graphs? Anyone on the phone have any questions? Ask now or forever hold your peace. All right, that's fun. So, all right. So for each of those object formats, which are output by the compiler, they actually typically they use the same binary format that your well-formed final executable actually uses. So you have different names and different structures for different operating systems, binary formats that they use. So COF, or Common Object File Format, was introduced with Unix System V. PE is actually derived from COF. PE is what Windows uses, and that's what we're going to be going over a bunch. And then your Unix derivatives like Linux use ELF, the executable and linking format. And so actually you can see embedded in the name of ELF is the notion that this format is going to be used for executables, and linkable files. So your output object files from a compiler are ELF files, which the linker knows how to splice together. Your output files from the compiler on Windows are PE files, which the linker knows how to splice together into a final executable file. And Mac OS X uses the Mach-O format as well, which is different. And then here there would be a nice audio clip of Macho Man, but I would dance around a bunch, but it's so unfortunate we're not going to get to see that. All right, so there's different targets of compilation that you can have, right? So you can maybe want a standalone executable which requires nothing else except itself in order to run the code. And on Windows, that would be a .exe file, and on Linux and Unix systems, there's typically no such thing. And basically, the point of an exe file, an executable file, is just that there's actually two subforms of that. There's the fully statically linked executable, where you take all of the code for all of the libraries that it depends on, and you just blob it all into the same giant file. And then there's just your dynamically linked file, where it says, you know, I want my code to be whatever was in my compiled, my high-level language files, my .c files, and for any library code, that's fine. I'll import that at runtime. So exe can either really stand completely on its own, or more commonly, for space reasons and for those shared memory reasons and stuff like that we were talking about before, more commonly, the executable is going to say, you know, I have my code, and any library code I need, the OS loader should get from me at runtime. All right, and then you can have, so for those libraries which a executable can request at runtime, those are called dynamically linked libraries on Windows, or shared library or shared object on Linux. And so these, again, are something, you know, you can write the code, you compile it out, and then you say, you know, dear compiler / linker, I want you to generate an executable, or I want you to generate a library. And the code it generates and, you know, the way it structures the files will be slightly different depending on what type of target you're trying to compile to. Typically, the point of the shared libraries is that they're not allowed to be run by themselves, right? You can't just double-click on a DLL file and have it execute some code. Now, that said, on both these binary formats, the libraries will typically have a single function which optionally can be executed immediately when the library is loaded into memory. So if, you know, my WickedSuite app requests mylib1, if I have a DLL main in mylib1, immediately when the OS loader maps that into memory, yes, that's right, I have that. Awesome. So good. This is how it works. This one must be updated, but the other one's not. Interesting. All right, so the point here is, you know, if I click on WickedSuite app and it says I must, you know, have mylib1, mylib1 could have a DLL main in it where it says when the OS loader loads mylib1 into memory, it actually goes and it executes the code in DLL main, and on Linux it's in the init stuff. And so the point is, although they're not meant to stand alone in that, you know, if you double click on them, they do any code execution, anything which maps them into memory, you will get code execution there, and that has implications for things like DLL injection and security issues later. But we'll skip that for now. And then finally, there's a static library, but this is actually interesting in that I don't believe on either Windows or Linux the static libraries have the, you know, P or ELF format. A static library is basically, it's a library, so unlike the dynamic library where it's supposed to be called by the OS loader and loaded just in time, the static library is basically just, you take a bunch of .o files or .object files and bundle them all into like just one big blob of, you know, an array of .o files. Each of those .o files implements some functions in it, right? So for each .o file, each object file, it's going to have, you know, whatever functions it implements. With the static library, you just package them all up into one, you know, big array of O files, and then they have just a little header format on the beginning that says, here's how you walk through this array of O files. And then at link time, what you can do is you can link against the static library, and any code that's found in that static library will always be linked into your final executable, right? These don't have the option to run just at runtime. They have to be whatever code you import from something which is implemented as a static library, it'll always be copied into your binary, into your exe, or DLL. All right. Again, this. All right. So since we're mostly going to be talking, so we're all going to be talking about P in this section. So just the simplest thing is to know that, if you see files with these types of extensions, that's going to be a PE file. So you could actually open them in a editor which parses PE files, and you'd be able to see the different data structures that we're going to talk about. And as I said, I don't believe lib files. Yeah, if you go try to open up a .lib file, you'll see that it doesn't have the same structure as everything else, because it's basically just a bundled bunch of .o files.
All those .o files have ELF and...
Right. Yes. So good point. So each of the .o files is an ELF or PE file, but a .lib file has some sort of header structure before each of those independent ones, which you have to walk to figure out how to get to each .o file. All right, and then just, in terms of practical things, we're going to be using Visual Studio later on, like in other classes, in order to do a little bit of compilation. So in terms of where you actually specify in something like Visual Studio that you want an exe or DLL or .lib, it's just under the properties and under general. Say, I want an exe file, I want a DLL file. And why that matters, for instance, right, is the DLL files, I said, So I said that the DLL files potentially have that DLL main function, right? And we know that most exe files, you've got your main function is the first thing which gets executed. In a DLL file, the DLL main is the first thing that gets executed. So this is kind of just a hint to the linker saying, which thing should, when I compile this thing in the headers where it says the first place you should execute code is here, which name of something should I point at? Should I point at main? Should I point at DLL main? Should I point at something completely different? This just has, for the simple case where you want it either to be main or DLL main. And then it also changes like imports and exports.
Hey, Zeno?
Yes.
Recently, there were a lot of vulnerabilities related to the loading of DLLs and how they were being loaded, the location and stuff. Is there any way to specify where you can actually load DLLs from when you're developing Visual Studio?
Right. So the question was, is there any way to specify that like my DLL must be loaded from this location, like within the file itself? Good question. I don't believe so, though. I think that's the kind of thing which is handled at the operating system level, essentially. Right. So you always have those. You give some search path to the OS loader, and the OS loader says, okay, I'm going to search here, and then here, and then here, and then here. So yeah, that's really more about how the OS loader is implemented and where it searches. So I don't believe you can. Well, let me think.
I guess the best thing would probably be to check a checksum of the file or some kind of digital signature of the file before you load it. But I guess the location issue is still kind of...
Right, so the search path hijacking type of issues, I think we're going to talk about a little bit later. But there's actually two sort of related vulnerabilities. One of them is the notion that if you put something earlier in the search path, the OS loader is going to, it searches the path, and the first time it sees a file named blah, it's going to import it under some constraints. So there are some versioning information inside where if the versioning didn't match, it would not choose it. But if you're the attacker, you make the version be the right version. There's the separate issue is more about searching out onto network shares and things like that, where you'll actually load in files from across network shares, for instance. It's more like if something is, the issue with the second vulnerability, the one which is more recent, I think in like August-ish time frame, that had to do with some programs write themselves in such a way where they're searching for a file and so we're going to be using TView a lot in order to dissect the binaries. Is there a question? I like PE view because it's very close to the actual structure definition. The names are fairly close. There's not a lot of interpretation. So a lot of things, if you know PE, it's good to get interpretation so you can go directly to what you care about. But when you don't know PE, it's good to just have the one-to-one mapping of here's structure definition, here's what it looks like in the file, here's the literal values that are pulled. PE view, for the most part, it doesn't parse most stuff, but things it does are very helpful to like go through. Once you're comfortable with PE view and things like that, then the CFF Explorer, because this added actually some capability I've been more. Things like jumping into just any location in the PE file and then say disassemble this right now as code. It doesn't matter if it's code or not, just disassemble it as if it was. So that's useful for, you can look at the headers and you can say, well, this header says that the code starts at that offset. So now within CFF Explorer, just start disassembling that to see what it is. And then we're going to be using WinDebug in order to do user space debugging rather than class for those who type it over. All right, so a big thing of terminology here, which you're going to see a lot of in the PE format, RVA for relative. So what this means is it's relative to the base address where this module is loaded into memory. So a bunch of the virtual addresses within the structure definition, they're relative to the base address. So I said there's some place where it says, here's the first instruction of code that you should execute. That's given as relative to the base, right? So it'll say like hex 20, but you're not going to the address hex 20, you're going to the base address. Right, so let's say that something was loaded into 80000. If you wanted to go to the absolute virtual address 8000100, the RVA would be x1000. Take your absolute virtual address minus base address, and that's how you get a relative virtual address. All right, so first structure we're going to look at, this is the DOS header. So there's only a couple of things we actually care about in here. In these slides, the blue things are going to be the ones that we care about. I mean, there's more things you can care about once you dig into it, but for now, for simplicity purpose, we're just trying to highlight the big. So, the main things we care about are the magic at the beginning and the ELFA. So, EMagic is always set to the ASCII characters M and Z. We developed MS-DOS. All right, so EMagic is the first 2 bytes of the first header of the file. So the very first 2 bytes of any DOS file and then potentially PE file should be MZ. Okay. And so that when you're just like scanning through memory or something like that, and you see, let's say you're doing memory analysis or something like that, if you see like an MZ, you might say, okay, well maybe I should start interpreting the rest of this data as a DOS header. All right. But the real thing we care about in the DOS header is the last field, the LFA new, which is the file offset. So it's the offset into the file where the PE header is actually going to be found, or the NT header, or whatever you want to call it. So within this very last field, it's basically saying here's the offset into the file to get to my next data structure, which is the image NT header structure. All right. So this is the structure we really care about most of the time, right? The DOS header is just there to A, show that there's an MZ, that this is a DOS structure, and B, tell us how to get to this next structure. All right, so for this next structure, we actually care about everything here. The signature field is, 004550, which is ASCII PE in like little endian order. Yep, little endian order, right? So the 50 is the P, the 45 is the E, and then 00 like they're null terminators. Right, so that's that first D word. You should always see PE in little endian order there. All right, now these two things, the file header and the optional header, these are not pointers to structures. These are actual structures which are embedded in the NT headers structure. So the first one is the file header, and this has a couple of fields that we care about. All right, so number of sections, time, date, stamp, and characteristics. All right, time, date, stamp is a pretty interesting field, actually. It's a Unix timestamp, so it's the second since, the epoch, which is 1970. And so it's saying this many seconds have elapsed since, 1970, the beginning of 1970. This field is set at link time when you link a file together. So I go and I make hello world, I compile it, I link it. The linker is going to fill in this time date stamp field of the file header with my current time as, whatever my system clock says, however far it says I'm past 1970. Now, this can be sort of used, in some scenarios as a unique identifier for the given file, because it's saying, if I compile the file and I, literally change nothing and just go to recompile the file or rebuild the file, the linker will go through its steps. It'll create a new time date stamp for whatever my current time is. And so we can think of, whereas the version number for some file, say in the operating system, may not have changed because, let's say Microsoft says, nothing of significance has really changed here. Maybe we just fixed some code, but we still want to call it this version number. But for each time the code is recompiled, the time date stamp will change. And so you can differentiate, two versions of the file, even if they have, potentially the same size and the same name, right? But you could still potentially differentiate them based on the time date stamp. They may have different code internally, right? So a hash may be different. You could use a hash. But based on the time date stamp, you could say these are two different files. And, so this is actually used. So recently, this last summer, Greg Hoagland started recommending using the time date stamp as one characteristic for doing some attribution of malware in order to track attackers and things like that. So amongst many different fields in this in the PE header, he's taking a bunch of these different fields and saying, well, together all of these fields kind of tell me that it looks like there's this guy or this group of people who are all responsible for this class of malware, and this group over here has slightly different time date stamps and different debug information, etc. So you can use the time date stamp potentially in some forensic stuff. You can use it as another sort of indicator of whether maybe an attacker developed just custom compiled some code for you, right? Does the time date stamp on some attack tool that you recovered, does it say that it was compiled yesterday, or does it say it was compiled 2 years ago? You have to take it with a grain of salt, because anyone who knows that this field is there is going to go in and change it and randomize it or whatever. But even that, potentially, if it looks like someone's randomizing their time date stamps, that's a little signature of, oh, that group is smart enough to randomize their time date stamps. So anyways, like all forensic things, in isolation it's not particularly strong, but when used in combination with a bunch of other things, it can provide evidence. So, all right, next field that we care about in the file header is the number of sections field. So there's going to be a bunch of different section headers, which we'll talk about later, and how so there's going to be an array of them immediately after this NT header, and in order to know how many of those headers that are there, you have to look at the file header, and the file header says there's going to be an array of 4 or 5 or 2 or however many section headers, these actual header structures immediately after this NT header data structure. And then there's the characteristics field, and this has things like, it specifies that this particular P file is executable, or this one works with 64-bit, or this thing is a DLL and stuff like that. So there's these miscellaneous characteristics which will be specified in the file header. Now, you got to keep this straight, because there's going to be file header characteristics, there's going to be optional header characteristics, and there may be somewhere else as well. I don't remember, but question? No? Okay. But yeah, so these ones are not the ones that we're going to care about super much. Yeah, actually, the section header has characteristics, the file header has characteristics, the optional header has characteristics. We're not going to care about these ones super much, but the next ones we see are going to be things like ALSR and stuff like that. So, all right. And then here, these are just a couple fields that we don't really care about, but I'm just putting that description there, and I'm not even going to talk about it. All right, so we said there were only 3 things we cared about in the file header, really. Number of sections, which I said is there's an array of these data structures immediately after the NT header. Number of sections tells you how many. Time date stamp, that's set at link time, tells you, what time the person compiled and linked this. And characteristics says whether this is a DLL, whether it's 64-bit aware, and stuff like that. All right, so moving on to the optional header, which is the other big structure in the NT header. All right, so this has a bunch of fields, and luckily we only care about a few of them again. So, let's see. All right, yeah, and the optional header is not at all optional. It's just these first couple headers, these are the ones which are born of COF, basically. So in the original COF format, there was a file header and there was an optional header and stuff like that. So it was just for extensibility of COF, and PE took it and ran with it. All right, so address of entry point. This is an RVA, right? So don't expect an absolute address. This is an RVA, relative virtual address, relative to the start of the module, where the OS loader, when it's done doing whatever it's going to do, the OS loader is, responsible for going out and finding libraries that it requires and stuff like that. When all is said and done and the OS loader is mapped everything into memory and it's ready to start executing your executable, the address of entry point is where it jumps to there and it sets the EIP to, the address where it calculates base address plus this RVA, puts them together and says, jump there, right? So that's where the OS loader starts the execution of the program. So you definitely want to know about this sort of thing if you're, for instance, debugging code. If you have some chunk of malware and you don't know where it starts and what it does and anything else, it's not going to have symbols. They're not going to compile it. So when we did the bomb lab in the intro x86 class, right, that had symbols. That's why you could see things like the name, phase 1, phase 2, explode bomb, things like that. It had the symbols with it because the symbols were saying this offset into here has the name, phase 1. Malware is not going to have symbols. Therefore, you need to know where the code is going to start executing. And so with a small caveat, you can guarantee that whatever this address is, if you set a breakpoint there, eventually the OS loader is going to load it and it's going to jump there. So that can be your first point. You can break there, you can start stepping through it, you can disassemble from there, etc. So when all else fails, you start with a breakpoint on address of entry point. Yes?
What's the caveat?
Caveat is thread local storage, which we'll talk about later. There's something which actually potentially can get executed before address of entry point. And if you don't know about that, then you set a breakpoint here, and that code executes, and it can screw with you, basically. So strictly speaking, this is not the absolutely first thing that executes, but almost always it is, unless you... So if we're talking reversing regular code, non-malicious code, this is definitely the first place, well, almost definitely. And for malicious code, if they're using some anti-debug tricks, there is one which we'll learn about later, which potentially allows them to execute code before address of entry point. All right. So size of image is basically telling the OS loader, read this field, allocate that much space in memory for this binary. The thing is, the binary on disk is almost certainly going to be smaller than the binary in memory. So when stuff gets mapped from disk to memory, typically there's alignment constraints and stuff like that, so some memory space gets wasted. And so size of image is basically saying you must have at least this much space in order to map this executable into memory. So that's just a hint to the OS loader, allocate that much space. So this is what I was just saying, section alignment and file alignment. So we said that there's those, there's that array of section headers after the NT header, which we'll talk about in a bit. But basically there's a field in this optional header that says when you're mapping those section information from disk to memory, you must always align them on this boundary that I specify here. So typically this is going to be something like hex 1000 because, as we saw in the intermediate x86 class, for those who had it, hex 1000 is the page size, right? It's the granularity that the memory manager uses to map, physical, it treats chunks of physical memory in hex 1000 chunks. And so typically what it, behind the scenes, the OS can map no less than hex 1000 bytes of memory at a time anyways. So it's basically saying, align it at the start of one of these hex 1000 bytes of chunks, one of these page aligned things. But it could be bigger than that. It could be not doing that at all, but it'd be interesting. I should probably run an experiment where I set the alignment to not 1000 and then see what happens, but see if it still maps. I have a feeling it would still map it to hex 1000. Anyways, oh no, that's not true. That's not true. Okay. All right. File alignment, on the other hand, So section alignment is about, like, let's take a chunk of the file off disk and move it into memory, and it must start at this base, address ending in hex 1000. File alignment is saying when this data is written to disk, it should not be written in chunks smaller than file alignment. So one common value for this file alignment value is hex 200, which is a sector on a hard drive, right? So 512 bytes is a sector. The atomic unit of hard drive, just like that hex 1000 was the atomic unit of memory. But I also see hex 80, and I have no idea what the significance of that is. So if anyone wants to go and find that for me later, find out why it would have hex 80 file alignment and say, I must write chunks of hex 80 bytes, I'd be interested in finding that. But basically it's saying, so the reason you care about file alignment, you need to know about it, is when the linker and compiler are generating those intermediate files, so when the compiler generates the O files, the file alignment potentially, could be big, and the file alignment leads to padding of the file essentially. The bigger the file alignment is, the more wasted space you potentially have. So if I have 1 byte to write to file, and the file alignment says I can only write 512 bytes at a time, then if I have a section that says my section has 1 byte, you can expect it to be actually 512 bytes. So we'll care about this file alignment in a little bit when we're looking at the way that memory is mapped. All right, and then finally, where is it? Finally? No, it's not finally. Image base. So this is basically the executable file or DLL, something like that, saying this is where I would like to be located in memory. So with this image base, it can specify a preferred base address. Now there's caveats to that in that, well, for one thing, what if your base address is already used, basically, right? If every DLL in the world says, I want to start at this base address, they can't all start at that base address. Therefore, the OS loader is responsible. It'll say, okay, well, I'll maybe give you the image base that you request, but if it's already used, I'm going to have to move you somewhere. All right, for executable files, the executable file has preference or has precedence in terms of what the OS loader is doing. So we saw that picture with like the crazy wiggly line saying that you click on Wicked Sweet App and the OS loader puts it into memory. The thing is, when you click on wickedsweetapp.exe, the OS loader gives preference to that and its image base. So it loads that into memory wherever it asks for, and then it loads the DLLs around it wherever they ask for if that space is currently available. So for executables, they pretty much, on XP type systems, not on things with ALSR, they pretty much can be guaranteed that they're going to be mapped into memory at their image base location. For DLLs, they'll get it if it's available. For system files, kernel drivers, OS loader doesn't even care. It'll just map them wherever it feels like. So yeah, that's the point with image bases. It's just saying, here's my preference. And then back in the day, Microsoft recommended that developers rebase their DLLs. So Microsoft themselves has taken their DLLs and run a tool that says, I'm going to try to put these as image bases that are non-overlapping. So it went through and it said, if I were to map all of these into memory, where would I put them such that they're not overlapping, so that they're not conflicting with each other, so that they don't have to be moved. And so Microsoft also recommends you take your DLLs and change up the image bases so that you don't have mylib1 and mylib2 both asking for the same address, because when something doesn't get the address it wants, that's when relocations have to come into play, and that's we talk about relocations much later. So, and then as I said before, Microsoft doesn't support position independent code, so it's always this image base has to do with assumptions that the compiler actually makes. So that if the image base is hex 80000, the compiler will potentially be assuming that that's the case when it makes addresses, and it'll assume that it must move from address 8000123 into EAX. And if you're not at 80000, that address is wrong. That address needs to be fixed up, and that's the point of relocations, as we'll talk about later.
Can a developer craft his own position in code?
Yes. So, right, exactly. The compiler won't give you position-independent code for Visual Studio, for instance, but you can write your own, and that's what you'll see when we get to the virus lab example. So, for the virus example, I had to write position independent code because the virus just tacks itself onto the end of files, and it doesn't know how big the files are going to be. Therefore, sometimes it could be at offset, 8,000. Sometimes it could be at offset 1,000. So it has to be position independent. All right. So this is the more interesting characteristic field. This is in the optional header. There's something called DLL characteristics, except it's not only applicable to DLLs. It's for anything. And there's a bunch of security relevant options here, basically. So the first one is image DLL characteristic dynamic base. This is actually how address-based layout randomization is implemented. Well, it's not how it's implemented, it's how you say my executable supports ALSR. So if this field is set in the optional characteristics, it's telling the OS loader, okay, you can go ahead and move me around in memory. If this field is not set, then the OS loader should give it its preferred image base. So, and specifically inside the Visual Studio, as I'll show in a second, there's a dynamic base linker option, and when you set that, you set the dynamic base linker option, and that sets the image DLL characteristics dynamic base flag within the DLL characteristics field of the optional header in the PE file. All right. So just as a miscellaneous thing, this dynamic base in and of itself, so I said executables assume that they're always going to be, well, by default executables are going to get their preferred image base, but if you're writing an executable on an ALSR compatible Windows version, you need to now, whereas previously it would just assume I'm going to get loaded to wherever I want to get loaded, it wouldn't have any of that information about how you fix it up if it needs to get moved around. So if in the case of only for an executable, which would have assumed otherwise that it gets its preferred base address, you must also use this linker option /fixed no. That's saying this executable will not be fixed in memory. You need to generate the relocation information to move it around in memory. DLLs always generate that relocation information. System files always generate it, but executables don't unless you give it this fixed no. So just setting this DLL characteristics, this dynamic base option for an executable will not make it ALSR compatible. So other options that are security relevant are force integrity. That's basically saying, OS loader, do not let this code run unless you check its digital signature. Yes?
So just out of curiosity, if you were to set that to no, if you were to take some signed binary and change that to false,
Right.
it would not get checked, right? And so it really, I'm just asking, is it that easy to bypass, or is there some other trick?
I believe it is that easy to bypass, because what would be the difference from taking a signed binary and turning off that flag versus taking a signed binary and stripping off the signature, right? If you assume the attacker has access to the file, they could strip the signature off. So, yeah, I believe that would just bypass it. Yeah. I haven't checked because I don't have any VMs that have, like, well, no, I guess, yeah, I could use code signing. I'll try that out later.
Yeah.
I think you can, like, try, well, I don't know if it enforces it, though. Like, Process Explorer has a digital signature on it, but I don't think XP is trying to actually check it, so.
I think there is a way to force the OS to only load executables with a signature.
Even on XP?
I don't know about XP.
I know for sure on, like, Vista and newer, but I don't think for XP, but I don't know, so. All right, let's see. Yeah. All right, so we're just going to go through that. All right, DLL characteristics NX compat. This is telling the OS loader I'm compatible with setting the NX bit, the data execution prevention. Well, DEP is what Microsoft calls using these bits which are in the x86 spec now. Right, so in the intermediate x86 class, we talk about the NX bit and where it is in the page tables, but the point is just it's a bit that you set in the memory map that says this chunk of memory is non-executable. If someone tries to execute any code on this page of memory, throw an exception. So the thing is, developers do all sorts of weird stuff, so Microsoft had to gradually roll out DEP compatibility, because if they just locked down and started enforcing DEP, if they just said nothing on the stack may ever execute, nothing in the heap may ever execute, some real legitimate code would stop working. Things like Adobe Action Script interpretation where they, dynamically, just in time, create code and they put it on the stack and then they execute it in whatever heap, I think. But anyways, if you set the NX compat linker option, it'll set this flag in your DLL characteristics, which will say to the OS loader, go ahead and mark my non-executable stuff as really non-executable, where it should not ever be executed, right? Otherwise, it'll be potentially executable stack, and that's where, if you have a stack-based buffer overflow and they put code on the stack and then they can execute it. If you have NX or dep enabled, then unless they found some other way to disable the dep, then they shouldn't be able to execute code on the stack or heap or whatever. And then finally, the characteristics no SEH. The structured exception handling is a method that Windows uses for catching exceptions, so the user space code can catch, like, if, it can register a handler that says, if I get a divide by 0. Again, in the intermediate x86 class, we talk about interrupts, and we know that, a divide by 0 will actually cause an interrupt. The OS will catch the interrupt, but then the OS can, like, pass interrupts back down to the application and say, hey, can you handle this? Can you deal with a divide by 0? And I can register in my code a structured exception handler that says, yeah, if I accidentally divide by 0, I'll just fix something up and continue on. The thing is, structured exception handlers are on the stack, and they're a target for buffer overflows. So if you can buffer overflow far enough, even in the presence of stack cookies and stuff like that, you can cause corruption of the structured exception handlers, and that's just another way to get arbitrary code execution. So this no SEH would basically say, dear OS loader, don't ever try to pass, structured exception, don't ever try to pass interrupts down to me to handle, because, attacker could have maliciously, overwritten them or anything like that. So the attacker could have created a fake one, basically. So, right, and then again, this is just, these things, they're mostly one-to-one. This safe SEH is the one for, actually that's not for the no SEH, so I'm not sure on that. All right, in Visual Studio, for instance, so where you would find the things for ALSR and dep and stuff like that is under the properties and then under linker, and then it looks like under advanced. So under advanced, under linker, under properties in Visual Studio, there's this randomized base address thing where you can see it says dynamic base. If you set that to true, then it's saying my binary is ALSR compatible. If you set this data execution prevention, it's saying, my thing is dep/NX compatible. And then this one right here, this /fixed no, that's what you need to set on executables in order to actually make them ALSR compatible. Because otherwise they won't generate relocations information. And yeah, so if I compile, so this, for this configuration right here, if I compile it and I go look into PEView, so this is sort of the basics of how PEView is laid out. We have, the executable name, the DOS header, which I could go in and look at all the fields there. And then the NT header, we said the NT header has a signature, a file header, and an optional header. If I go into the optional header and I scan down, there's this DLL characteristics, which is interpreted for me, and it says, okay, you have this, bit right there set, and that's the dynamic base bit. And you've got the NX compat bit, and you've got some other bits, terminal server aware, and you've got relocation. So this is how I can see that, each of those compile options, link options, ultimately led to a binary that has certain characteristics based on what I gave as input. All right, so, yep, before we go on, it's lunchtime. So, back 1 hour lunch back here at 1:05.